All right, so we left off, this is where we left off on Monday, and we're talking about our document generation model. There is a correction I need to make. RJ here is not all the unique words, but it's just straight the number of words in document J. Okay, so what we are working on is a document clustering model. Okay, and the idea is, we have some documents which is we're going to treat as a bag of words. Okay, so it's kind of as if you've got this document and it, I don't know, in some kind of cartoon fashion, it's like you shake the page and the words fall off into a bag, right? So that's kind of the bag of words model. And so if you think about how that works, then the underlying structure doesn't matter, but it's just what kinds of words show up, how many times they show up. That's what's going to kind of differentiate one document from another. And so as far as what words appear in the bag, we came up with this document I'm using this paper, and I've posted this paper on CCLE. It's kind of long. It's called Gibbs Sampling for the Uninitiated, but really just I would say you can start in section 2. Section 1 is all about just the Gibbs sampler in general. It might be good. It's good to read as just like see another author's kind of explanation for it. Okay, and section 2 is this application we're going to use Gibbs sampling for this document clustering algorithm, and so part of that is we need a model or an idea of how words in a document or in a bag are generated. Okay, and so what we said is that first of all, there's going to be some kind of Bernoulli distribution that we either you flip a coin or you do something, and if it comes out heads, you're going to generate a document about, I don't know, fruit, and if it comes out tails, you're going to generate a document about sports or something. Okay, and so that Bernoulli distribution itself, that parameter pi comes from a beta distribution, right? So you have a prior distribution for that Bernoulli parameter. Maybe it's a coin that lands heads, tails 50%, or maybe it's a coin that lands heads, tails 80%, right? 80% of your documents are about fruit and 20% are about sports or something. This is a silly example here. And so anyway, whichever one, what document it is given this label, right? So label 0 if it's about fruit, or label 1 if it's about sports. We could expand this into a Dirichlet distribution where you can generate, like a category, one of several categories of documents. Okay, but anyway, once you have this, then we are going to generate the words that appear in the document. And which words appear in the document is defined by this probability vector theta, wherever my cursor is down here. The vector theta, which is however many words there are in the language, or whichever ones you're willing to track. Okay, so maybe there's 1,000 words that you want to track or something. You would have a length 1,000 vector theta. And all of those values in theta would add up to 1, and so that's a random production of a Dirichlet distribution, which we said is kind of the multi-category generalization of the beta distribution. Okay, so I'm hoping this feels okay. So we talked about the beta and the Dirichlet distribution, and so. So once we have this, we get theta, and so using, you're going to say like, this is how many words I need in my document. My document has 600 words. We're going to use a multinomial distribution, okay, and produce some kind of set of outcomes there, right? So it's kind of just like you can roll a a die 600 times, and you're going to count how many times did the face 1 show up, how many times did face 2 show up, how many times did face 3 show up. Here it's similar. I'm going to generate 600 words. I'm going to generate a random word 600 times, and the word banana shows up 6 times, and the word apple shows up 7 times, and the word sport shows up 3 times, or whatever, you know. And all of these other words show up with these frequencies. Okay, and that's what we have. And so this is the plates represent each document. There's n documents. Each one has its own label, and then within that document there are r sub j words. Okay, and which word appears is determined by the multinomial distribution. Is that okay as far as this diagram representing the generation of documents? Okay, and so again, this is I drawn straight from this page here. Okay, in the handout. Okay, except it's there's not as much text. Okay, but the one thing I greatly appreciate about this paper that the authors wrote is that they have a table defining every single one of their variables, which is very, very useful, because as you're reading through something, it's very easy to just ask, wait, what does this thing represent? And so this is very handy. Okay. Okay. So once we have that, now we are going to generate. Now we have to kind of come up with our Gibbs sampler, right? And so the Gibbs sampler is going to draw a random value for each parameter. Okay, and there's a lot of parameters for us to estimate. And so to do that, we're going to draw things from conditional distributions, right? So how many values are there to draw? You're going to have an L value to draw for each document. Okay, so let me kind of just define our Gibbs sampler. Okay, so we take a multivariate distribution and convert it into a series of univariate distributions. Okay. And so if you're able to do this, right, you generally get better performance with the Gibbs sampler than other things, right? So kind of side note, they say Markov chain Monte Carlo is often the least desirable way to generate a sample. Okay, that's a bit of a joke, in that if you can use any other method like inverse CDF or something, if you can do that, is generally preferable. But Markov chain Monte Carlo is kind of the least favorite way, but sometimes it's the only way that we can do. And so and then as far as the Markov chain ones, we're looking at the Metropolis Hastings, and the Gibbs sampler. And Metropolis Hastings, those again are going to be less preferable, but sometimes it's not possible to do Gibbs. Okay, if you're able to do Gibbs, and that if you're able to kind of separate things out into univariate conditional distributions, that's the hard part, is figuring out the conditional distribution. If you can do it, you're going to get good performance, which I think you saw in your homework, right? So when you compare just kind of the multivariate Metropolis versus the Gibbs sampler probably converged to that. Like both of them, you started off with terrible starting locations, and then the Metropolis algorithm took a little while to explore until it finally got to a region of good samples. And then the Gibbs sampler I think it gets to the good samples fairly quickly, right? And that's related to just kind of this thing. But again, for the Gibbs sampler, you had to figure out your conditional distribution, which I hope I helped out by linking that paper. But if I didn't link that paper and I said like do the math here, I feel like the homework would have gotten like much harder. I don't know, maybe not. You still had to read, right? Okay. So anyway, what we're going to do is we're going to convert it into a series of univariate distributions, and so there's a bunch of things that we have to sample, right? We're going to sample basically each document label, and we're going to sample the distributions of theta. Okay, we could try to sample the pi's as far as the parameter for flipping the thing, but what we're going to actually do is we're going to integrate that out, and there's some math there, right? So parameters in our model. So basically we have theta, the word probability vectors. Okay, and then L sub j, each document label. So if you have a ton of documents, you've got a lot of these things, okay? And then pi, which is the kind of probability of class 0 or 1 document. Okay, but we're going to integrate this out. Okay, yeah, so implementing an effective Gibbs sampler does require some mathematical manipulation, okay? But by kind of putting in the effort to manipulate things into univariate distributions, you get major performance boosts, which is important. Okay, let me just make sure I'm not missing anything here. Yeah. Okay. All right. So and so that there are n of these things. Okay, so our total joint distribution is going to be a product of a lot of things, right? So we've got, this is page 10 of the handout, 10 of the handout. Okay, we've got the so this is the probability of this pi parameter. Okay, so this is coming from a beta distribution to determine the parameter pi. All right, and then we're going to multiply this by kind of the probability of all of these document labels, right? So you've got the vector of document labels, and what kind of distribution is this? So once we're given the probability parameter pi, the L's come from what kind of distribution here? A Bernoulli, right? So this is going to be kind of a product of Bernoulli's. Bernoulli distributions. for each label L sub j, okay? And then we have a theta 0, okay? This is based on some gamma 0. So what distribution generates our theta 0 vector? So theta, what is theta 0? There's two of these. Theta 0 is the word probability vector, okay, right? It's the vector of all the word probabilities that sum up to 1. That comes from which distribution? What was that? The Dirichlet distribution, right? So this is going to be a Dirichlet distribution. Right, and then we have two of these theta things, right? We got a theta for document class 1 and a theta for document class 0, okay? And each of these have you know, come from a Dirichlet, right? So this, we have a Dirichlet and another Dirichlet. Right, and then from there, and then we have to do all of the words, okay? And so to kind of the simplified notation of saying all the words will kind of get captured in this corpus 0, corpus class 0, given the theta 0 vector and the labels, and corpus class 1 given the theta 1 vectors, or the theta 1 vector and the L's there, okay? So these are basically all of the words in the documents, and these come from a multinomial distribution. All right, so far so good? Okay, so when we do all of this, basically each of these things, you're going to have the beta distribution, and so basically pages 11 and 12 kind of just write out the PDFs. So I'll just, as you read through the document, okay? So pages 11 and 12 in the document write out the PDFs for, you know, probability of pi given gamma pi 0 and gamma pi 1, and then so this is the beta and the L's given the pi, and this is Bernoulli, okay, and then this one, the vector theta given the gammas, this is Dirichlet. So it just, all it does is it writes out the PDFs for all of these things, and this one's multinomial, the last one being multinomial. So it looks scary, these pages, because there's lots of PDFs written out, right? I don't know, maybe it's just me, but anytime I see a whole bunch of math formulas on a page, it's a tiny bit intimidating, right? But here, these are all the PDFs, okay? And so that's what those pages are. Okay, and then on page 13, they integrate out pi. Okay, so this is again, it feels a little bit scary when you look at all of these integrals that appear there, but basically they jump. It's so that we can avoid having to sample for pi. Okay, so I'm gonna just show you what the math looks like. Okay, and so the math, again, you can follow it. I would say the authors do a very good job of explaining every single step. But you know, as you're reading this, if this part seems a little bit too crazy, don't sweat it too much. Okay, you can follow each of these steps, and they take each of these things and they say, okay, well, this is the beta distribution, and if I plug in the PDF of the beta distribution, I'm going to get this thing, and this part's the Bernoulli distribution, and if I plug in the PDF for the Bernoulli distribution, I get this. Okay, so this is the beta part right up to here. Okay, so this is the beta, and then this part over here, this is not the d pi, but sorry. Let me just see. Okay, so this part up to here is kind of the beta distribution, right? This is beta and this is Bernoulli. So that's what we have. This is beta and this is Bernoulli. Okay, and so they just kind of do this and they move things around. They say, all right, well, what is, they deal with the gamma function. They actually do a proper treatment of the gamma function. And they say, okay, well, if you move all of this around, then you're going to get this, okay? Which feels a little bit crazy, okay? But what we can see here is, you know, they're combining the terms that are kind of in common here, okay? And it feels a little bit messy, all right? But it does simplify the actual Gibbs sampler. And again, when you build up a Gibbs sampler on your own, it often requires some of this mathematical manipulation, okay? And so it can be intimidating when you're out on your own, right? And if someone says, like, try to build this thing, and you got to think and wrestle with it, okay? All right, but we're going to come back here, and now we're going to build the Gibbs sampler here, and we're going to try to generate each of these things from the respective conditional distributions here. Okay, so you know, this is just a recap of the Gibbs sampler. Okay. So let me just talk about how do we go about sampling each of these things. Okay, so we integrate out the pi. Okay, and now we're going to actually talk about the Gibbs sampler. Okay, so what we want to do is for each document, we need to sample a value L, okay? All right, and so the conditional distribution of LJ, which is the label L for document J, is going to be the probability of LJ given, okay? And this is going to be all the document labels, all the other document labels. Okay, so let's say you have 20 documents, okay, and you want to know how do I sample the third document? It's the label, okay? You're going to look at the document labels for documents 1, 2, and then 4 through 20, okay? So everything but the one that you're trying to sample for, okay? So this is all the other document labels, okay? And it's going to depend on all the other document labels. Basically, all the other, the corpus are basically all the words in all the other documents. So the corpus for everything that's not in document J, okay? So all of the words or corpus, not including document J. Okay, and then the vectors theta 0, the vectors theta 1, and all of your other hyperparameters, okay? Okay, and so this is going to be equal to the probability of this document label, okay? These are the words in document J, okay? And then it's a joint probability of everything else, okay? Everything else that appears in the numerator. And then the hyperparameters. The document calls the hyperparameters mu, okay? Which feels a tiny bit confusing because every time I say mu, I always think mean, but it's just a way to kind of capture all of the hyperparameters together. Okay, and then because it's a conditional, it's all of this divided by the given stuff, which is going to be the probability of basically all the given stuff. The J, the C, and the minus J. Okay, everything but to that. The theta 0, the theta 1, and the hyperparameters, okay? Okay, and so if you take a look at what this is, okay? If I combine Lj, Wj, L minus J, and C minus J, this just becomes the entire corpus and the entire set of labels, okay? So Lj plus L minus J is just equal to the entire L, and then Wj plus the corpus of everything but is just equal to the entire corpus, right? Okay, so anyway, that simplifies to the entire thing, the theta 0, the theta 1, and your hyperparameters mu divided by everything that's in the given part. Okay, so how does this end up going, okay? All right, so how do we go about this? Well, it's going to end up coming from a, basically a, we want to draw a Bernoulli distribution, okay? And what we're going to do is the posterior distribution for this thing ends up being, okay, Okay. Bernoulli distribution, okay. With basically kind of this p equal to kind of basically the probability of class 0 divided by, well, I guess I shouldn't say so kind of looking only at the numerator, okay, I'm gonna just call this kind of the value of class 0, and it's gonna be value of 0 plus value of 1, okay? And this is gonna become the probability of class 0. This value is basically proportional to the likelihood after the fact here, okay? So basically the probability of getting LJ saying equal to 0, given all of the other values, can be found to be in the hyperparameters. Okay, is going to be equal to how many documents are in 0 plus kind of your pseudo counts, minus 1, divided by n plus times the product Okay, so let me just kind of break this down, all right? So, so this C0 part, this is basically equal to how many docs are currently labeled 0. So this is kind of like the prior part, okay? How many documents are currently labeled 0, plus you have your pseudo count in the beta distribution, right? So this is, your shape parameter 1. If you think of your shape, the two shape parameters in the beta distribution, you can kind of think of those as the pseudo prior counts, okay? So it's basically how many documents are currently labeled 0 plus the pseudo count in the beta distribution for class 0. Okay. I'm sorry, is there a question on one of these terms here? This is all documents, the number of all documents, plus the kind of pseudo counts, total pseudo counts, minus 1. Okay, that's going to be gamma pi 0 and gamma pi 1. Okay, this part you can kind of just think of as a prior. So this is, and then this part over here of x, this is basically the multinomial likelihood. Of all the words in document J. So let me just, I'm going to try to explain this, give a little bit more intuition. I mean, I could just leave you with this, and all you have to do is just plug in numbers, and you'll get what you need, okay? But I want to just try to give you a tiny bit more intuition with this, okay? So this is the result that we end up sampling, okay? This thing, I'm going to just go ahead and snip this into, okay? Because what we need to do is we need to just sample a value, and it's either going to be a 0 or a 1, right? We just want this part. Okay, so again, this we can think of as the prior. And so we can think of, you know, if we start with beta 5 comma 5, okay? And we'll say at our current iteration, so beta 5.5 will basically says that, you know, basically about 50% class 0 and 50% class 1, right? Something around there, but there's some leeway, okay? And let's say at our current iteration, okay, we have 20 documents and 18 are labeled 0. Okay? So based on just your current information, what's the probability of being class 0? It would be 18 over 20, around 90%. Okay? But you're kind of also going to temper that with your original prior distribution, which said 5.5, right? So this leads to something around 90% class 0 and around 10% class 1, okay? And so, so this becomes, you know, Cx plus gamma pi x minus 1 is going to be 18 plus 5 minus 1. And we're going to divide this by n plus gamma pi 1 plus gamma pi 0 minus 1. Okay, and this is, we have 20 documents total, plus 5 and 5, kind of our pseudo counts that we had earlier. All right, and so we get something around 22 over 29, okay, which is, I don't know what that is. 22 over 29, somewhere around 76%. Right? So this is kind of based on just our current counts and our beta prior. Before we look at any of the words, we're going to guess that it's going to be around 76% chance of class 0. Okay? So this is kind of our prior probability of being class 0 before we look at any words. Okay, so that's what we have there. And then the other side, okay, over here, this is just the likelihood of getting each of the words. Of getting this particular bag of words. Right? So let's say we have apple 10 times, banana 10 times, what, ball 1 time, and points 1 time, okay? And so under theta 0, which is about fruit, I don't know, this could be like 0.4, 0.4, 0.1, 0.1, okay? This is the fruit vector. and theta 1 is going to be 0.1, 0.1, 0.4, 0.4. That's the sports vector, okay? And so kind of our product is going to be, 0.4. So the product for theta 0 is going to be 0.4 raised to the 10 times 0.4 raised to the 10 times 0.1 raised to the 1 and 0.1 raised to the 1, okay? So versus the product for theta 1 is going to be 0.1 raised to the 10 times 0.1 raised to the 10, 0.4 raised to the 1, and 0.4 raised to the 1. Okay, and we can see this thing is going to be much bigger than this one, right? So kind of given our current vector of word probabilities, because apple and banana showed up so frequently, we're going to say the likelihood for this is much higher, okay? And so the resulting Bernoulli, okay, we're just taking advantage, again, just like we always do with this stuff, is that we're only worrying about the numerator, okay? We're not going to worry about the denominator. And so we calculate the numerator for both possible values of our label 0 and label 1, okay? And that's what it says. Find basically the numerator for label 0, find the numerator for label 1, and then we scale those so that they end up summing to 1, right? So you just take the sum of the numerators as your denominator to get your posterior distribution. That's all this is saying, okay? So this is basically the result of the numerator is right here. You can think of this as kind of the numerator, all right? And this says basically calculate the numerator for all possible values. Okay, and then the denominator is equal to the sum of the numerators. So we take advantage of that, and that's how we get our kind of our posterior distribution for sampling sampling the labels. Okay, and then the other part is sampling the thetas. Okay, so how do we sample our theta? Well, okay, again, kind of just using our Bayes rules and the kind of ignoring that we have to take out the denominators, we can say it's going to be proportional to basically the numerator part. Okay, and then this theta is going to come from a Dirichlet distribution, right? So what is the Dirichlet distribution? Okay, so it's very similar to the beta distribution. So if you recall the beta binomial, do you guys remember the kind of the end-up relationship that we had? So if your prior was, say, beta, I don't know, 81, 219, okay? And then we observed 4 success and 6 failures. What's the posterior? It ends up being what? 81 plus 4 and 219 plus 6, right? You just kind of add each category to their respective prior categories, and so we get 85 and 225, okay? That's how it worked for the beta binomial. Okay, we're basically doing the same thing, okay? For the Dirichlet distribution, okay, now you have a bunch of categories. So in our case, maybe we have 4 categories. In our super simplified vocabulary, we're only looking at 4 words: apple, banana, ball, and point, okay? So our prior distribution is going to be a Dirichlet with kind of prior counts. And so maybe I've got it all evened out, 5, 5, 5, and 5, right? And this is going to be kind of the prior pseudo counts. Okay, apple, banana, point, or ball, and point. Okay, so these are kind of the prior counts for each of the words in our vocabulary. Right? Okay, and then basically for theta 0 is going to come from a so our observed will have, okay, so maybe with our current thing, we will have observed for the fruit documents. So this is going to be corpus 0. Okay, maybe we've observed 20 instances of the word apple, 17 instances of the word banana, 2 instances of the word ball, and 1 instance of the word point. Okay, so these are the counts of words in docs labeled 0. Okay, and so our theta 0 will come, our posterior distribution will come from a Dirichlet with what? We're going to take these things. 20 plus 5 is 25, 17 plus 5 is 22, 2 and 5 is 7, and 1 and 5 is 6. Okay, and this is going to generate some vector of theta, right? Okay, and then maybe your observed counts, observed corpus for document 1, or of class 1, maybe we'll have 3 instances of the word apple, 2 instances of the word banana, 18 instances of the word ball, and 16 instances of the word point, okay? And so theta 1 will come from a Dirichlet with the 5 and 3 is 8, 5 and 2 is 7, 5 and 18 is 23, and 5 and 16 is 21. Does that kind of make sense? You know, the relationship, so if you understand the beta relationship, beta and binomial relationship, then the Dirichlet multinomial relationship, I feel like is just a natural extension where you just add kind of more categories here, okay? It's just when you do it on the computer, you don't have a simple vocabulary of 4 words, you're gonna have like 1,000 words, okay? In your homework assignment, okay, I picked kids' books, okay? So kids' books have small vocabularies. So one of them is Green Eggs and Ham, which is known to have like one of the smallest vocabularies possible, okay? And then the other one is Go Dog Go, which also has a very small vocabulary. So I think there's a total of 59 unique words after you remove stop words. And so it's very simple, and you'll just basically apply this. There is pseudocode, all right? A large part of it, oops, where did the pseudocode go? Okay, this pseudocode is provided. This is very, very helpful, okay? And you'll try it out. It'll probably converge within 5 iterations, which is remarkably short for a document clustering thing, but it's because we're using these children's books, okay? But the impressive thing is, I think, is that you're gonna start off with completely random labels. Okay, it doesn't know which documents belong to Green Eggs and Ham and which documents belong to Go Dog Go. So it has no idea, but when you apply this algorithm, it's going to find the clusters, and it's going to say these books often have, these documents have the word eggs and green and ham a lot, so we're going to cluster them together. These documents have the word dog and stuff a lot, and we're going to cluster them together. And it's going to discover the clusters very quickly, for this toy data set, which I think is rather impressive for just an algorithm where we're just applying the Dirichlet distribution over and over again. Okay, we'll end there. On Friday, I'll talk about the final exam, and we'll see you guys then.